So this is the home of my projects. The Sir James Spence Institute, and it's part of the Royal Victorian Infirmary in Newcastle upon Tyne. That's where I map and model primary bone cancer. So I say I, but it's really we, because this has been a collaborative study and involves colleagues from Leeds, Newcastle and Oxford. The project wouldn't have been possible without funding from the Bone Cancer Research Trust and the North East Children's Cancer Research Fund. So this morning I aim to give you a flavour of what is, in reality, a complex and methodologically challenging project. I've also brought 2 posters with other aspects of the work displayed, and if anybody wants to discuss them, I'm quite happy to stand there for hours talking about it. So, but for now, I'm going to continue by putting the type of research we do into context. So, from a research perspective, we need to know more about bone cancer because, unfortunately, it is still really poorly understood. To increase our understanding and find a cure or cures, we have to look at it from all different angles and on all different levels. From the molecular level, and I'm really looking forward to Sue's telling her tales later, through to the individual as well as population level. And that's where this research fits in. I'm involved in epidemiological studies that focus on health event patterns in populations in different geographical areas. This type of study is the cornerstone method of public health research and informs evidence-based medicine. So, isn't epidemiology brilliant? Right, I'm going to use this as an example to show how brilliant it can be, and hopefully you'll feel that way by the end of my presentation. So John Snow, he was an anaesthetist and a skeptic of the miasma theory that was dominant at that time. And according to this theory, cholera is contracted through breathing in bad air, like an invisible fog. The cholera outbreak of Soho became one of his most famous studies. He carried out real boot leather research and went round talking to the local residents. He identified the source of the outbreak at the water pump on Broad Street. Snow took lots of chemicals and microscopic samples directly from the pump, but it wasn't these that convinced the council to remove its handle. It was his studies of the patterns of the disease. This is the original map created by Snow, and the white area demarcates the main affected areas. And as you zoom in, you get more and more detail. Patterns become apparent, and each of the black dashes here represents a death in a household. The cluster around the pump is clear. So with the help of a reverend who was well known in the area, Snow managed to conduct door-to-door survey and found out that all the cholera cases had drank water that had came from that pump. So what about our study? The principle's the same, but the technology has improved since then and has enabled consideration of much larger areas and much larger populations over time. Snow would have used an awful lot of boot leather now doing the study I've just carried out. So it's a small area analysis because when you look at the population at high resolution, you can see much more detail. Some important factors could be masked at a lower resolution. There are 12 main authors in the study, and they contribute the necessary skills base and data sets that made the work possible. So in a bid to add to the etiological, the causal evidence base, and after researching the literature, we aim to test the following hypotheses. That the incidence of osteosarcoma is associated with deprivation and or population density, and the incidence of osteosarcoma is it related to the level of fluoride in the water supply. I didn't realise how apt the Snow example would be here. So then we did the same for testing for Ewing sarcoma. The analysis would be carried out at a small area at a level, and that's census wards for England and Wales and postcode sectors for Scotland. And there's an average population in those areas of about 5,500 people. So how did we do it? So in outline, there was a complex ethics application. Rob's just mentioned about how sometimes these can hold the process of research up. My ethics application took 9 months to complete, and the project was supposed to be finished in 12 months. So data was collected from a number of different sources, and I'll go into more detail on the following slides. Preparing the data sets was another mammoth time-consuming task. Again, I'm going to go in a bit more detail about this aspect of the research to give you an idea of what the process entails in the slides that follow. When we did the analysis, which once the data is set up doesn't really take that long, I am not going to go into detail about the analysis itself, but I'm going to report the results and the conclusions. So what data did we use? The data request for England and Wales was coordinated by West Midlands Cancer Intelligence Unit. And again, Rob's pointed out now they are the lead cancer registry, and it does help in the time consumption of these types of process. The data for Scotland required a separate ethics application to the Information Science Services for Scotland to enable the data to be released by the Scottish Cancer Registry. So we've got a number of data items in the whole that were all led by the ethics process, because we had to ensure that individuals couldn't be identified. So these are the overall number of cases for osteosarcoma and Ewing sarcoma diagnosed between 1980 and 2005 for Great Britain. And you can see that the peak falls within the 15 to 29-year-olds age group, which is exactly what Rob found with his studies. So, the denominator data, we needed to know the facts about the population living in the small areas under study. We used the census for this, so we are starting to build a data landscape consisting of 4 levels. So you've got the denominator data, and then you've got incidence data falling on top of that. But we're also going to be looking across time, so the 1981 census, the 1991 census, and the 2001 population census. There are also data sets available that are derived from the population census, and we use things like the Townsend Deprivation Index to give us an idea of the deprivation in the levels. And these have been used to measure levels of deprivation for studies of healthcare need. So postcode directory data was also used to join all the information together. And we also collected digital boundary data so you could create maps in a geographical information system software package. The fluoride data, we also had to have lots and lots of fluoride data. And we got that from the 24 water companies operating in England, Scotland and Wales. The Drinking Water Inspectorate gave us the data for England and Wales, and we had to do a separate application for Scotland. So what you've got now is a lot of data. The actual folder now is about 118.6 gigabytes. And I just want to give you an example of what that is. 100 gigabytes is probably equivalent to 100 complete Britannica encyclopedias. It could also fill a floor of a library in academic journals. Just for illustrative purposes, this is a GIS. So what I've done is I've shown you the different components of the actual system. On the right, you've got the map lying underneath, and at the moment it's shown a layer of postcodes for the whole of the country. At the front, you've got the table that lies behind that map, and you can see that highlighted in red, there's 1.5 million records. So you can imagine there's no way you can deal with all that information just by looking at the tables. On the left-hand side, you've got lots and lots of layers of information, and literally lying on top of each other and lying to the sides of each other as well. So it becomes quite complex and needs to be managed efficiently. One of the problems is that as much as it would be lovely, you get all of these layers of data, as much as it would be lovely for them all to fit neatly together, it doesn't in reality. So I've tried to put this slide in so you can see the mishmash that you end up with. And we had to find a way of being able to harmonise this information and read it more readily. I've tried to make a transparency so that you can see the actual wards and the water supply zones all intermingling, and also you've got disparities between the layers, but also across the layers, because even the water supply zone data didn't match perfectly together. So let's just illustrate what we tried to do, and I'm just going to focusing on a method that we've built for this, and it's going to be useful in so many other projects and not just with bone cancer. I've just for illustrative purposes again, this is a map of fluoride across Great Britain. Levels of fluoride across Great Britain. The blue parts are where there's artificial fluoridation programs in place. The rest, it's naturally occurring fluoride. And you can see again how when you zoom in, you start to get more and more detail. I think where the blue is like water supply zones, and you can see, I hope you can see that they don't actually match with the underneath. And therefore you can't make comparisons and you can't read the data together as a unit. So when you focus in, you can see again the blue here, how it falls across, and then this one's a really weird shape there, right? Sometimes you can have up to 5 water supply zones supplying one census ward. So what we did was we got the postcode data and joined it on the top of that. And again, this is zoomed in. This is the same type of data that you've seen before in the big map, the green blob. But as you zoom in, you see the detail. And you can actually see it's literally the housing estates here with the postcodes. So you can see that it wasn't distributed evenly across. So we've now weighted the postcode, the population according to its distribution, and we've now been able to allocate a fluoride level for each census ward, which can be used to answer whether or not fluoride has effect. So the results, again, these are the statistical results, and I don't want to go into details of these, other than to say that these are the relative risks of getting the whether there's any relationship with osteosarcoma and Ewing sarcoma. And we found that there was a relationship with osteosarcoma with a Townsend deprivation score, and then with Ewing sarcoma there was a significant relationship with population density and non-car ownership, which is zooming into Townsend deprivation score. No statistically significant association was found between osteosarcoma or Ewing sarcoma and fluoride in levels of drinking water, you'd be pleased to know. In conclusion, lower incidence osteosarcoma was associated with greater deprivation. Higher incidence of Ewing sarcoma was associated with living in densely populated areas and greater levels of car ownership. This study contributes to the growing body of evidence linking risk of Ewing sarcoma to some aspect of agriculture. Further studies of environmental exposures or land use may be informative, and we're preparing the applications at the moment. So again, we've got no significant relationship, but this is the first time that it's ever been studied across the whole of Great Britain at census ward level for England and Wales and postcode sector for Scotland. After adjustment for age and gender, no statistically significant association was found between osteosarcoma or Ewing sarcoma and fluoride levels in drinking water. Just like to thank many, many people for allowing this project to be possible. And thanks very much for your time.